All right, geometers, welcome to the first lesson of the year. Our focus for today is going to be on points, lines, and planes, and specifically also on how to apply these for linear measure. So what I'm going to do is start by giving you a very quick explanation of this upside down triangle and what we're intending to get you to understand by that. And so really we're looking at the building blocks of geometry. And the foundation of the building blocks of geometry are actually points, lines, and planes. That's mentioned at the bottom. Those are our undefined terms. And the thing to understand here is that none of these have any actual size. And that's a kind of a strange concept. And so I want you to imagine the following hierarchy. When we think about space, we think about 3 dimensions. And so I'm going to just squeeze the word space in here. And so space is everything, all points around us, 3D, length, width, depth, or length, width, height, lots of just different ways to express it. Contained within space, what we have is an infinite number of planes or surfaces. And what we know about planes or surfaces is that planes or surfaces are two-dimensional. They're flat surfaces. You can move with length and width, but you don't have any depth or any height. Okay, and then if we move down the hierarchy, contained within planes, we have lines, and by definition, lines are one dimension or one direction. They continue forever in both directions, but of course, when we say both directions, it's along the same line, and there's only one dimension. And then at the bottom of that hierarchy, lines themselves are, of course, made up of an infinite number of points. And if you were to follow this hierarchy down, of course, you should be able to ascertain then that the dimensions of a point are 0. They have neither length nor width nor depth. And again, this is the foundation on which we build definitions. And so it's hard to imagine these, but these are our undefined terms because we refer to them as being undefined terms because they don't actually have any size. We use each of these terms in turn to build definitions. We use definitions to write rules and postulates. A postulate is basically just a theorem that we don't really need to prove, and I'll introduce you to one of those today. And then from those, and including the undefined terms, the definitions, and our rules, we build theorems, which we're going to spend some time this semester and next proving. Okay, so that's a quick introduction. Now what we've got is a series of definitions. This really is the starting point for the language of geometry. You do need to know these definitions so that you can speak geometry and you can understand in a theorem that talks about a segment versus a line versus a ray, that there is a distinction. And so we're going to get a little more into that in future lessons, but you need to be able to speak geometry, and that really means you must make sure you understand these definitions. So as I mentioned before, we've got a point. It has neither shape nor size. It just represents a place in space. Down here is space. That, of course, is 3D. And then we build, in this case, upwards, no dimensions, 1 dimension, 2 dimensions, 3 dimensions, and we move from a point through to space. Specifically, we're going to look at some key phrases that we're going to use in today's lesson. One of them is collinear. So if you break that apart, co as in share, linear as in line. And so points that are collinear are points that share the same line, just like these ones A, D, E, and C. Coplanar, same logic, they share the same plane. An intersection is the set of all points that are shared or in both figures. And so when you have 2 lines that intersect, they're going to intersect at a point. And we'll get a little more into that in the examples below. Very quickly, a segment is just a subset of a line. It's a piece of a line. And what it has is 2 defined starting or ending points. And its length is measurable. And finally, we have congruent segments. The key here is to look at the symbol, which is really just an equal sign with a wavy little piece on top. That means congruent. Mathematically, it's the same thing as equal, but later on we'll explain the significance of the difference between equal and congruent. It's important, particularly when we talk about triangle congruency and when we talk about proofs. Okay, so quick little fill in the blank to see if we understood the hierarchy of dimensions. And so when we have two lines that intersect, they are going to intersect as highlighted above at a point. Some people would argue you might have one line, let's pretend that's a good representation of a line, and the other line lies right on top, and then you could argue that two lines intersect in a line. If that's the argument you make, that's a good argument. I would argue that's only one line, but argue with your teacher if you need to. If you can make a good case, then we'll consider giving credit or partial credit. Okay, when we have a plane and a line, those should intersect. And so if we move up here, here we have a representation of a plane. Let me just make mention of the fact that we have to represent a plane in this way, but of course there are no defined edges on a plane, even though we have to draw it as having defined edges, and that is because we are using a 2D representation and we have got limits. And so in theory, of course, those are going to continue forever in all of these directions, and there is no edge to a plane. Okay, so if we look at that as a plane, and so I'm just going to use this one, we might have a line that is contained within a plane, or we might have a line that passes through a plane, and that should hopefully help you to understand that the answer to this question, a plane and a line intersect in a point, but we might also accept the answer line in this case because the line may be contained within the plane, and therefore every single point on the line is an intersection. Lastly, we have two planes. If two planes are going to intersect, hopefully you realize that two planes will intersect in a line. Two planes cannot intersect in a point because, of course, planes continue forever in all their directions, in all their 2D directions, and therefore planes don't have any ending points or edges where they could intersect another plane. Okay, so let's jump ahead here. So what we have is this first notion, and really what we have is the first introduction to the idea of a postulate, which is just a rule which does not need to be proved because it's self-evident. So in the figure on the right, we have this word that we use in the context of geometry. The word is between, and what we mean by between really is that the points that are between, so point C is between point A and D. What that means is it is collinear, and it means it lies on the segment, the line segment joining A to D. Point E is given here as an example of something which is not between A and D. Of course, in terms of a description, we might say E is between A and D, but in geometry terms, E is not defined as between because it is not collinear. It is not on the same line or line segment as A and D, and therefore cannot be between. Okay, and the postulate basically says this: if C is between, then the length AC plus the length CD gives you the length AD, which, like I said, is sanctioned by logic. The sum of the two parts must equal the whole. Okay, next example. I'm rushing because I'm going to try to keep this down to 15 minutes if I can. So in the next example, what this is an attempt to show you how in 2 dimensions we represent 3-dimensional objects. Okay, and so this is intended to be a pentagonal prism sitting on plane X with line GH, which is passing through plane X. Okay, so line GH is not contained within plane X, it is passing through plane X. Okay, let's go ahead and give the answers to these examples. You've been asked to name 3 points of intersection between a line and a plane. And so the obvious and easy one, of course, is point G. It is the point of intersection between GH and plane X. Others that are maybe less obvious because the diagram does not make it obvious that it's a line, but in fact, point C, D, E, and so forth are all points of intersection. Those points of intersection are contained within the following lines. So FC, even though it is drawn only as a segment, of course, is part of a line FC, and therefore point C is a point of intersection between line FC and plane X, and the same logic for points D, E, B, and so forth. Okay, next question. So the question is, are points H, G, and F coplanar? And very often students in this particular case will say no, and unfortunately that is the incorrect answer. The correct answer in this case is, are those points coplanar? And the answer is yes. The common mistake that's made is they're assuming that the question is asking, are points H, G, and F coplanar to plane X? But actually that is not part of the question. And so if we were to take I'm going to get my highlighter tool here, and I'm going to join F to G to H and back to F. And what you need to realize is that is in and of itself a plane. We have plane FGH. You need at least 3 letters to name a plane. And therefore any 3 points will lie in a single plane or be coplanar. You have to have at least 4 points which are before you can entertain the possibility of them being non-coplanar. Okay, we're going to name an intersection between 2 planes. So again, the previous example should give you a little bit of a hint as to how to approach this one. So you can look at F, C, D, and using the same logic, this is one of the faces or sides of my prism. This is in fact a plane, and so we have plane X intersecting plane FCD, and it's going to intersect along line CD. So an intersection between 2 planes would be, of course, we know from the previous example, when 2 planes intersect, they intersect in a line, and in this case, in the diagram, CD, line CD is the intersection between plane FCD and plane X. And once you know that, of course, we have a multitude of other options. We could say line FC was the intersection of plane FCD and FCB, and so forth. So many correct answers, but it did ask just for one of them. Okay, and then next question, name the intersection between AD and GH. And so I'm going to just join A to D, and so that line is going to go along there. And the catch here is for you to realize that even though that might continue and appear to intersect GH at some point, the answer is they do not intersect. And that, of course, is because line AD is contained within plane X, line G is passing through plane X, and so if they don't intersect on plane X, they're not going to intersect at all. Okay. Moving on, basically what we're going to do in these 2 examples is we're going to use the segment addition postulate. That's the one that says the sum of the parts of a segment must equal the whole. What I'm going to do is pause the video occasionally here just so I can wrap this up in 15 minutes, and I'm going to write the setup down. Okay, welcome back. So you can see all I've done for both of these examples is just sketched out what the given information gave us. We have Q is between P and R, and that means it's collinear, lying on the same segment. We were also told that QR was equal to 8 and PR was 17. The question asked us to find the measure of PQ, which means PQ's length. In this case, relatively straightforward. We can just say PQ is equal to 17 minus 8, which is equal to 9. So if the sum of the parts equals the whole, then whole minus part must give you the other part. The second example is very similar. Same setup, Q is between P and R. The difference is we're given one additional piece of information. PQ is equal to QR. That's the notation that you use. And what that allows us to know is that this must also be 2x minus 1 because they're equal. And our equation that we can set up is as follows. 2 multiplied by 2x minus 1 must be 3x plus 3. And now we can solve. Okay, very quickly, so I've solved this. We obtain an x value of 5, and then I substitute that in to the expression for PQ to get our final answer of the measure of PQ.